notes or whatever, yeah. Yo.
Is there just like no way for, if it's infinity minus infinity, is there just like no way to look at it and figure out? Or is there like a super secret trick you're not telling us?
I mean, I think the super secret trick is just the algebra.
It's not really a super secret trick.
Yeah, it's not.
Just like math.
Yeah. Sorry. Something good happened? Oh. Whoa. Ooh. Damn. Well, you did something smart, guys.
Oh. Wait, why is there
Actually, this is
one
better if you just do it the cool way.
Yeah, this is, yeah.
I don't know if that's smart, I have to do it the cool way. Wait,
What?
you gonna,
Or you gonna watch me do bad algebra?
no, I take it back, I'm gonna do it now the cool way, I'm not smart. So Eob wants to redo the problem that we just did a minute ago, but now he wants to do it by completing the square. So this problem that we just did, if instead you complete the square on 4x squared plus x plus 1, then,
Plus half, right?
no, that has to be like 1/64th, isn't it?
No, one.
Yeah, it has to be 1/64th, the way I did it at least. Because it's like half of a fourth is an eighth squared. Right, but then what I just did is I just added 1/16, so I need to subtract 1/16. Okay, so when you're all done, you end up with 4x plus x over x, wait, what? X plus an eighth. Yeah, I'm having trouble completing the square for some reason. Plus 15/16, which you could leave like that, or you could write it as 2x plus a fourth. Did I do that right? Squared? Isn't that the same thing? No.
No.
Yes.
Wait, why did you didn't?
What?
Oh, never mind.
Because 4 is like 2 squared, so you just, yeah. Yo, that's right, yeah? Okay, whoa, that was some challenging algebra 1 just happened, but I have emerged with the correct answer. So, Eob says we could be really cool, and we could instead write this as minus the square root of 2x plus a fourth squared plus 15/16. And then we truly can ignore the 15/16 because it is like sort of not growing, right, or something like that. Yeah, so it is truly irrelevant in the face of this. And so this is really like 2x minus, might as well be 2x plus a fourth, plus some insignificant things. And what happens as you take the limit as x approaches infinity of 2x minus 2x plus a fourth, it goes to negative a fourth. So that's pretty awesome. Well, cool. How you guys doing on these two problems? What should we do here? No, I don't think I need to multiply the conjugate here. I think I can just. That's not what I did, right?
I multiplied by 1.
Really? Why do we have to? I don't feel like we don't have to. Can I just divide the top and bottom by the highest power of x in the denominator?
Yeah.
Yeah, that's what I'm going to do. So the highest power of x in the denominator is x. And so if I do that, I get the limit as x goes to 0 of 1 over 1 plus 1 over x minus, and now we have that same situation again, right? Where 1 over x needs to get put back in jail. He becomes 1 over x squared. You guys understand what I'm talking about?
Yes.
Okay, good. Can never be totally sure. And so to end up with is that. So is the answer just, wait.
1 over x.
Oh yeah,
It's 1 over.
oh yeah, because that should be x.
1 over x. 1
1
over
over
x.
Oh yeah. Yeah, so I guess intuitively speaking, this guy is like irrelevant, right? Because x is growing so much faster than root x that, or is it? Oh, hold on, I don't know what's going on now. Yeah, so 1 over x. Anyway, let's see what happens. So we put 1 over x squared in. So yeah, you're right. You're all correct. It is 1 over x. It's 1 over x squared. And so what's happening is this. These are both just going to 0, right?
But we're
No.
finding
What do you mean no?
X
approaches
approaches 0.
Oh my God, what am I doing?
Okay.
That whole last 4 minutes was just nonsense to be stricken from the record. So no, you're all right. I need to multiply with a conjugate. I got that thing I was just doing.
It's pretty easy if
I was just doing the wrong limit. I'm sorry. So you're all correct. I definitely do need to multiply with a conjugate. So let me just shut up and do that. All right. That's 2 orange cards for me. Huh.
Yeah, you can just factor out an extra log and just multiply it all out.
Yeah.
Yeah, you're right. And then, oh, from here, I just posted 0. Yeah. I don't think we need to do it.
So, yeah. Yep. I can cancel the x out, just like you said. Now, finally, it is not indeterminate. And so the answer is 2?
1.
1, really?
Is it
No,
all?
2.
Oh, wait, no, it's 2 over 1.
I think it's 2, because that's going to 0, that's going to 0, that's going to 0, so it's like 1 plus 1. So it's 2 over 1.
It's a lot easier to use y equals root x plus 1.
Yeah, I agree. I got 2. Someone back me up. Okay, good. And then how about this problem? Do you guys get to this yet? What makes this one weird? First, use your intuition. What should the obvious answer be?
It's like infinity over infinity.
It's like infinity over infinity. Can I get an answer though? What do you think the answer is?
I'm taking the answers that we know the first time.
1/3.
1/3?
Negative infinity, so negative 1/3.
Alice thinks it's 1/3.
Oh, negative infinity.
Oh, it goes negative negative.
Yeah, so I agree that this is growing really, really big or something, and this is more or less kind of like x, and this is more or less like 3x, so 1/3 seems reasonable. But we're taking limit as x approaches negative infinity. So that means x, if you plug in like negative 1,000,000, when you square negative 1,000,000, you get 1,000,000 squared. When you take the square root, it's going to be approximately 1,000,000. But the denominator will be approximately negative 3,000,000. So now I expect the answer to be negative 1/3. Steven, you with me? Yeah, so how can we actually do this? So if we divide the top and bottom by the highest power of x in the denominator, then this is going to turn in the denominator, I'm going to get 3 minus 3 over x. That's pretty straightforward. Now we get back to that thing where I said that there was a thing that's kind of true. It's kind of true that 1 over x is just root 1 over x squared. In particular, this is true when x is positive. But it is false when x is negative, right? When x is negative, then the square root of 1 over x squared is negative 1 over x. That's just because, I don't know how to put this, like fact of algebra, you know, the square root of x squared is, well, in fact, it's actually just absolute value x, right? It's x if x is positive, but if x is negative, if you take a negative number like negative 3 and you square it, you get 9, take the square root, you get 3, so what you're going to get is the opposite of the thing you started with. And so via this fact of algebra, when I rewrite 1 over x, it gets converted into negative root 1 over x squared. You following this? This was like in preparation for putting back in jail. Essentially, I am making the careful arithmetic argument that these two things in the red boxes are the same. And the reason why this is a little bit more subtle is because now we're taking the limit as x approaches negative infinity. So since we're taking the limit as x approaches negative infinity, x is negative, and thus I have to do this. Okay, so the point of all that is that then this becomes, when I combine the square roots, negative root 1 plus 4 over x squared over 3 minus 3 over x. And I'm taking the limit as x goes to negative infinity. And so this is going to 0, and this is also going to 0. And just as we predicted, the answer is negative 1/3. Okay, are we feeling good? Good. Whoa. What about the book work? Should we go over a little? There's like very little book work. Should we do like a problem? Laura, let's do a problem. Yeah, 37. Should I do it, or should we have someone else do it? Is there anything else besides 37?
No.
Okay, then let's just do 37 and call it a day as far as homework-wise. So 37. This was on page section 2.3 or 2.2. Which page?
76.
Oh, this was kind of like another chance to do the same thing over again that we did in last class, right? More or less. We're taking the limit as x approaches to x squared minus 3, and the directions say find delta such that blah 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 blah. What they are essentially giving us is epsilon equals 0.01, delta equals you tell me, right? Is that a good summary? Okay. So let's make a graph of this. First of all, the answer is 1. Right? Yeah. So 1, 2, 3, 1, 1. Wait, no. Uses, what's wrong? Okay, good. Alright, so here I have a high quality graph of this situation emerging, and what is happening is that someone is challenging me with an epsilon picture not to scale of, this is almost the exact same problem, right? Picture not to scale of 0.1, so this is like 1.01 and this is 0.99. And what I have to do is I have to figure out, all right, how close do I have to get to 2 to ensure that within delta of 2, my values will be within epsilon of 1, or within 0.01 of 1. Cool? Okay, so I think I can just do this the exact same way I did last time, right? Let's just solve for x by saying, when is this function between 0.99 and 1.01? Is this what you guys did, basically? Yeah, and now I can just do it. So x squared minus 3, 0.99, 1.01. Now I'll add 3 to all 3 sides of this, and so I will get 3.99 is less than x squared is less than 4.01. Take the square root of both sides, and so the grand conclusion is that whenever x is between root 3.99 and root 4.01, I'm good to go. And that should strike you as being very reasonable answer, because right when x is exactly 2, it's 1. So this number is a very tiny bit less than 2. This number is a very tiny bit more than 2. What's up?
That's what I got. The point is the different answer.
Yeah, I think that.
Yeah,
I
the
think
book
the
is-
delta, the biggest delta.
Okay. Can we just ignore that? I remember this now. I need to make a mental note to add something to tell you to ignore the back of the book in this case. This is what you guys did? Okay, can I just finish this off? So finishing, so what's it turns out that the answer is, which one of these is closer to 2? This one is, right? And so did you guys all just say, let delta be root 4.01 minus 2?
Yeah.
And then you looked at the back of the book and you got confused.
That's what the book had. It was just in decimal form.
That's what the book had?
Yeah, it was
No,
a
it had it in, like,
decimal.
a fraction.
It was just a decimal. No, it was like 1/100 divided by 5 equals 0.00.
Yeah.
or something.
It was like 0.002.
Yeah.
That's like if you put that in the calculator, that's what you get.
Well, that's because of
They might have chosen a rational number that's
Or
within that.
maybe-
Anyway, this is the answer, so I'm happy. If you're happy, I'm happy. Okay, good. Can I have your homework right here?
Yo, my good friend, yo. My good friend.
Wait, we did this?
Maroon, can you erase the backboard?
We did this.
Wait, are we? No, the
What's the book called?
Oh, it's
Do you want limit one? Whether economic globalization.
What's up?
Do you want
No, I don't think I need the worksheet because we kind of went over the whole thing, so. The bookwork, which is pretty short. Yeah, there just wasn't that much work, so I.
It's the text is live. Don't worry.
Oh, that's great.
Alright, good. So that'll be like the last time that happens all semester. Thank all those positive feelings about me. For the dark nights when you're. Alright. Good. I want to talk about a new theorem. It's a very exciting theorem. It is called.
Does it have, oh, it has a name.
It has a lot of exciting names. Yeah, it has a name. Not only does it have a name, you like when theorems have names. It has multiple names. It is called, one name of it is called the Squeeze Theorem, which is pretty exciting. But it is also, well actually, first let's talk about what it is, and then I'll explain to you the other names. So, what's up? It's pretty cool, yeah. I mean, there's so many cool things, I can't keep track of them all. Alright, so here's what the Squeeze Theorem says. The Squeeze Theorem is a theorem that you use. Remember how last class, was it last class that we did all those limit laws? It was last class, right? Yeah, and we talked about how there's like all these formal laws which can be proven with epsilon delta proofs, etc., etc. But some limits are just too weird. In order to prove them, sometimes you just can't figure out what a function is doing, but you can maybe figure out what a different related function, pair of functions is doing, and then this function just goes along for the ride. So let's draw a picture of a situation in which there's some function f which is doing some kind of weird thing. Let's say that. Alright, so there's my function f, and the function f is the function that I care about. And specifically, I care about what f is doing at point C. Alright? But I can't figure out what f is doing at point C. But there's a different function, let's call it g, and this different function, though it may be doing different things, near C, it is bigger than my function f. So let's call this function g. And function g, certainly at least according to my picture, is bigger than f near C. Okay? And furthermore, there is a function h, and h, who knows what h looks like, but near C, it is a little bit less than the function. Okay, so this is my claim. So claim, okay, so I'll just say if the function f that I care about can be bounded below by a function h and above by a function g, and then I'm just going to write on some open interval, containing C. In other words, nearby C, this inequality holds, leaving that a little bit vague at the moment, right? If nearby C, that inequality holds. And if, so I'll just write if again, so there's like an and, if the limit as x approaches c of this lower function h is L, and the limit as x approaches c of the higher function g is also L. Now here comes the conclusion of the theorem, but maybe you know it already. I have three functions, g on top, f in the, I need to like rewrite this. I made this like, it's too weird, this picture. G on top, f in the middle, h on the bottom. So if I have these three functions, which when I get very, very close to c, f is between these two. And what happens to the lower function as x gets really, really close to c, it gets really, really close to L. And so does g. Then what must f be doing at c?
Also.
Also L. Yeah. Then the limit as x approaches c of some function f is also L. Basically.
I get what.
Yeah, of course you get it. Because basically what is happening is we don't know what f is doing, but we do know that g and h are respectively bigger and smaller than f, and they are both going to the same point. So if these two functions are both going to the same point, then the behavior of f is squeezed between the behavior of g and h, right? Follow? Okay. This is called the Squeeze Theorem. It also goes in different textbooks in different countries. Some people call it the Sandwich Theorem. Which, anytime food can be involved, I like that. The Sandwich Theorem, why is it? First of all, I think there's no H in sandwich, right?
No.
Strange. The Sandwich Theorem says that, well, it's the same theorem, right?
Yeah.
It's called the Sandwich Theorem. Because it's kind of like you have a function sandwich, right? F is in the middle, and F is like the, you know, pastrami or whatever. All right, and G and H are the bread. It also, I think in French they call it, but except I don't know the French word, the prisoner theorem. How do you say prisoner in French? Does anyone know? It's like a what?
It got so
It got so dark. I was thinking of the French.
Sandwich.
Yeah. Squeeze, like a big hug, sandwich is like food, still pretty good, and then suddenly we're all in jail. Yeah, the prisoner there, because it's kind of like F is the prisoner of G and H, right? Like, it's like one of those old cop buddy films where like they have to escort a guy like across country, so they handcuff, you know what I'm talking about? So it's like two guys and they handcuff the prisoner to them, and then anywhere at G and H go, F has to come along for the ride. Good. How do you prove this? So hard. Okay, proof. I'm just gonna write so hard. It is in the appendix. It is a some nightmarish epsilon delta proof that I don't even want to think about. I've never even done this one. I've never tried. All right. Great. What can I do with this? With this, I can prove quite rigorously, if we assume that this thing has been proved by skipping it. Then suppose someone asks me for the limit as x approaches 0 of x squared sine 1 over x. What do you think this is?
I don't know.
Fortunately, you are like, you guys are in the top 0.001 percentile of experience with obscure, strange functions like this.
Oh, that's this thing.
Take a moment and sketch yourself a picture of this function. We did almost this. We did something very similar.
This theorem's helpful.
We did almost this. We did x sine 1 over x. We did x squared sine x. And we did all the things that you need to be able to graph this have been given to you, but we never graphed this actual function before. This is weird? Just by weird you mean awesome, then I agree with you. Yeah. So talk to me about this function. Can you like say something?
It's really weird for 0. It's like
It's odd. Yeah, that's true. It is odd. What else? Envelope, yeah. Exactly. Yeah. Facts. Fact about this. Well, okay. So fact about sine 1 over x. Sine 1 over x is always between -1 and 1. That's a true story. And then I can multiply all three sides of that by x squared, thus giving me negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared. So Kendall is telling us that whatever else this function is doing, it must lie between these two parabolas. So
Theorem for that.
we have what?
I said if only we had a theorem.
Yeah, if only we had a theorem for that. Hold on. I'm still graphing, but yeah, you're right. So what does this function look like? It's going to be doing its business between these two parabolas. Now, I'm going to just leave it as vague what this function is doing when x is large, because I'm not particularly interested at the moment. Because what I'm interested in is what it's doing near 0. So let's just like kind of, I'll just put a question mark because I don't care. I don't want to talk about that right now. I don't want to talk about end behavior. What I want to talk about is 0 behavior. What's it doing near 0? Yeah.
It's like squeezing towards 0. Parabolas just go closer and closer to 0, I guess. And so that means that.
Can I get a little more specific answer? Yeah, Ethan Chen.
Well, it's getting closer to 0, but not at like because sine of 1 over x is like periodic, so it doesn't really get there at a consistent rate. Although like x squared is getting consistently closer to 0.
Wait, more. Same 5 people keep raising their hands, but I guess I just have to call on them. Yeah, abuses. Cancel anyone.
It has like an infinite number of periods, but the closer it gets to 0, the smaller those periods are. The closer to 0 each.
The smaller the amplitudes are, right? Yeah, we know what sine 1 over x looks like, right? This is the go crazy, this is the go insane at 0 function, right? So it's still doing that. It's just that it's doing it enclosed inside these two parabolas, right? So this is like a man who is going insane, just like before, but now he's like in a straitjacket or something. So he's like being, he's like screaming and crazy, but he's not really going anywhere, right? And then I guess it's odd, so I better end like down here. All right. So I claim that this function looks like this. Do you agree?
Yes.
Okay. And says Rabbi Weissman, if only there were a theorem which would enable me to determine what this limit is, and the answer is the Squeeze theorem does. Because this function, I already bounded it by this function and this function. And it is just true, and can be proven rigorously if one desires, that the limit as x goes to 0 of negative x squared is 0, and then stop talking. And the limit as x goes to 0 of x squared is 0. So if the bottom function and the top function are both going to 0 and x equals 0, and my function is guaranteed to be between those two, everybody with me? Then my function, though it exhibits this insane behavior, which seems, I guess the idea here is that if you ask me to give an epsilon delta proof directly of this fact, I would cry. Okay? Do you appreciate how no one's asked you to do this, so you haven't yet like faced the terror of trying to do an epsilon delta proof with some insane function like this? You just can't do it. It's too hard. The algebra, I mean, terror, pure terror. But fortunately, via the Squeeze theorem, I don't have to, right? Because I can just compare it to known functions. All right, good. So that is great. The Squeeze theorem is used at one very crucial juncture in calculus, this class that we're in now, to prove one very, very important thing. And you might be disappointed because it's one very, very important thing. It's something that you already know. So, but what we are now prepared to do is give a rigorous proof of this thing that we have been assuming since last semester. And that is that thing that I've called the most important limit in all of calculus. And the most important limit in all of calculus is the limit as theta goes to 0 of sine theta over theta. And what is this? This is 1. All right. So we are now going to prove this. And we're going to prove it by not just drawing a picture and kind of waving our hands and saying, yeah, I feel like it's like, you know, da, 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 da. Now we're going to prove it like for real. All right.
How much space do you need for this?
How much space? Oh, big.
I hope.
But I write big. Yeah, no, you need more space than that. All right. So, also, I would like to remind you, I feel we've had this conversation before, but we're going to have it again, that this argument if we're going to prove this properly, must be a geometric argument. And that is because the sine function is a function which we defined geometrically. We defined sine to be the function such that if you have a unit circle and you draw the line x equals 1, and if you give me an angle whose arc length is theta on the unit circle, then sine theta is by definition the height. It's the y-coordinate of the endpoint of the arc of length theta. And this is, you will recall, back in probably like pre-calc A, when Giles explained this, that he had to like first sort of obliterate any concept of degrees from your consciousness, and would probably just insisted throughout pre-calculus that we do trigonometry in radians. And the big reason why we do trigonometry in radians, one reason is because it's just better, even for pre-calculus. But for calculus, it is like essential. For everything that follows, it works only if you do your trigonometry in radians. And in particular, it is only in radians that this picture is correct, right? Otherwise, you have a totally different picture. Okay. Okay. And if you do calculus in radians, you get beautiful things. And if you do calculus in degrees, you get terrible, disgusting things. So you would just never do calculus in degrees. All right. This is the motivation. Now let's do the proof. All right. So for the proof, we have to first establish a geometric relationship. So I'm going to redraw this situation, but much bigger. Okay. So I will pick. So let's take an angle. Let's see. I don't know. Just yeah. Let's take an angle theta. Let that be theta. And then I'll draw this thing. So I can also think of this little angle as being theta. Then I can drop a perpendicular, and this is sine theta. Okay, looking good. Theta is length of that arc. And now I want to get tangent involved. And so what I'm going to do is I'm going to extend this ray out, and I'm going to construct a tangent at the point 1, 0. So that's like a right angle. And I will mark the point of intersection. Everyone good with this picture before? I feel like you've seen it before. If you had a good teacher, this is how you proved the Pythagorean identities. And what is the length of this thing right here? It's the length of this segment between these 2 points. Oh, I thought you would just all know this immediately.
Oh, it's like.
Oh, wow.